Hi, welcome to this lecture series on data structures. Today, I'm going to talk about one of the applications of the Stack abstract data type called as conversion of Infix expression to Postfix expression. Now, what is an Infix expression and how does it relate to a Postfix expression? An infix expression is of the form a plus b, where the operator is in between the operands, and a postfix expression is of the format ab plus, where the operator is placed after the operands are written. This expression, which is the infix expression, is more human friendly. So it is easier for humans to evaluate infix expressions, whereas the postfix expression is more computerly, which means it's easier for computers to evaluate these expressions. The infix expression is not computer friendly because of inherent ambiguity present in the infix expressions. For example, if you have an expression a plus b star c, the operand b is associated with two operators, plus and star, and it is difficult to know which of these two expressions are used to evaluate a plus b star c. So the first possible evaluation would be a plus b and then multiply the result with c, or it can also be a plus b star c. So for a computer, it's difficult to determine when it is trying to parse this expression whether to associate b with the plus or the star, and hence when it is done parsing a plus b, it doesn't know whether it has to evaluate a plus b or wait for the result of the further expression evaluation and associate b with that result. In contrast, the postfix expression is unambiguous, so corresponding to every evaluation of the infix expression, you have a unique postfix expression. So for this particular infix expression, postfix expression takes this form, and for this infix expression, postfix expression takes the form ABC star plus. In the case of the infix expression, one of the two possible evaluations of the given infix expression is determined by what is known as the precedence of operators. For postfix expression, the precedence of operators is already built in to the expression. So for every possible combination of relative precedences of all the operators, you have a unique postfix expression that a computer can evaluate in a single parse or in a single scan. There is a rule called BOD Mass, which is used to associate precedence with various operators. So B stands for bracket, O stands for OF or power operator, D stands for division, M stands for multiplication, A stands for addition, and S stands for subtraction. So according to the BOD Mass Rule, if you have an expression a plus b star c, it is evaluated in the following format. Star has higher precedence, so b star c is computed first, and then A is added to the result of b star c. Bracket has the highest precedence in infix expression. So if you have an expression of the form a plus b star c, this is evaluated with brackets, any expression inside the brackets being evaluated first, and then the whole expression is evaluated after the expression inside the bracket has been evaluated. You also have the concept of associativity, which is used to determine the precedence of same operators occurring twice. So if you have an expression of the form a plus b plus c, associativity dictates that you either evaluate the left operator first and then evaluate the right operator, or you evaluate the right operator first and then the left operator. The first form is called as left associativity and the second form is called as right associativity. Plus, minus, star, division are all left associated operators, whereas exponentiation is a right associated operator. So if you have an expression of 2 exponentiation 3 exponentiation 2, because exponentiation is a right associated operator, you would evaluate 3 exponentiation 2 and then try to evaluate the rest of the expression. So they'll lead to 2 exponentiation 9, which is 2 power 9. Contrast this to the left associated evaluation, which would give us a result which is different from 2 power 9. So in the left evaluated precedence, you would do a 2 power 3 power 2, which will give you 8 squared. So this is different from this number. Let us take an example of an infix expression and see how we can convert the infix expression to a postfix expression. So you have a plus b star c plus d exponentiation e exponentiation f. So anything inside the bracket takes higher precedence than the rest of the expression. So I convert a plus b to the postfix form, which is ab plus. Also convert the c plus d into its postfix form, which is cd plus, and copy the rest of the expression as it is. So after the first step, we have expression 1 star expression 2 exponentiation e exponentiation f. We see that we have 2 exponentiations in the expression, and because exponentiation is right associated, we will have to evaluate e exponentiation f before the left exponentiation. So your expression would be e1 star e2 exponentiation e f exponentiation, which is the postfix form of this infix expression. And again, we have a scenario where the star and exponentiation collide and exponentiation wins because it has higher precedence. So the next expression would be e1 star e2 ef exponentiation exponentiation. So this is the left operand and this is the right operand. So this is the left operand, this is the right operand for this exponentiation, which gets converted to this particular postfix form. And now you have 2 expressions, first expression being e1, the second expression being this e2 ef exponentiation, which gets converted to e1 e2 ef exponentiation star. Substituting e1, which is ab plus, substituting e2, which is cd plus, we get the final postfix form, which is as given below. To implement this particular conversion using stack, we have to define a few concepts. Define a stack for storing the operators which are parked while the operators of higher precedences are being evaluated, and where the expression is scanned by our program from left to right. So in this case, given the expression a plus b star c plus d exponentiation e exponentiation f is evaluated from left to right, which means we encounter the following operators in the order given. Star, we encounter plus first, then star, then plus. Obviously, we also encounter the brackets, and then exponentiation, which is power, and then power. So this is how we encounter the operators when you're scanning the expression from left to right. When you're scanning the expression, all the operands are immediately put into the output section, but operators are just checked if they can be immediately put to the output section, or they need to wait in the stack because there are higher precedence operators waiting to be evaluated. If you consider the precedence of open brace, open bracket, it is the highest, so you put it into the stack so that you can evaluate all the expression which is part of the bracket. And when you encounter any operator inside the bracket, they follow the normal precedence rules. So if there is no operator on the stack, or if the operator in the stack is in open bracket, you can put the operator onto the stack by default. Now, if you encounter operator that has higher precedence than the top operator present in the stack, you will be able to put the operator onto the stack. That's because this being the higher precedence operator would be the first to be output, because stack is essentially a LIFO structure, which means that the last input element, one that is first output. Last input element is the one that is first popped out. And another scenario is where you encounter a closing bracket, which would mean that you have to output all the operators that have been stored on the stack till you encounter a opening bracket. And what happens if there is already an operator present in the operator stack, which is same as the operator that has come as an input? In this case, we have the associative rules which break the tie. For right associated operators, because we are talking about this being the right operator and this being the left operator, because the scanning happens from left to right. For right associated operators, the precedence of this operator is going into the queue will be higher than the precedence of the operator that is already in the queue, in which case this would go and sit on top of the existing operator. But in the case of the left associated operators like plus, if you are comparing the precedence of the operator that's being currently evaluated and being checked if it can be pushed into the stack with the operator that is already existing in the stack, this would be less than the precedence of the operator that's already present in the stack. So which means you should have to pop this out and then push this into the stack, because the left operator which is already in the stack has higher precedence than the right operator that is just coming in because of the left associativity of the operator. I think we have covered the general form in which we are going to maintain or park our operators in the stack and when they are popped out. Let's try to resolve this infix expression using this heuristic and see if we can achieve the same output. So for every operator, we have two precedences associated with the operator, which is the in-stack precedence and the other is the out-stack precedence. So for opening brace, the in-stack precedence is the least and the out-stack precedence is the highest, because whenever you encounter opening brace, that should go and sit into the stack and has to be evaluated first. For exponentiation, the in-stack precedence, which is the left operator, will be less than the out-stack precedence, which will be the right operator, because this is right associated, or this honors right associativity. For multiplication and division, the in-stack operator, the in-stack precedence will be more than the out-stack precedence. So here you would get a 7 and then here you would get a 6, because this is left associated. For plus and minus as well, the in-stack precedence is higher than the out-stack precedence. So here you would get a 5 and then here you 4. So given this table, let us try to see how the operator stack changes and how the output is generated for our infix to postfix conversion. As we know, the input is scanned left to right, generating the following tokens: opening brace A plus B star, closing brace star, opening brace C plus D, exponentiation E, exponentiation F. Opening brace has highest precedence, goes to the stack. Next is A. A is an operator, A is an operand, so it goes to the output directly. Next is plus. Plus goes into the stack because in stack open brace has the least precedence. B goes to the output directly. Closing brace would empty out all the operators till the opening brace. Star would go into the stack. Opening brace has the highest precedence outside the stack, goes into the stack. C goes to the output. Plus goes to the stack. D goes to the output. Exponentiation. So we have another closing bracket here, which would empty out the stack again. So you have a plus and these are all wiped out. And you have an exponentiation. Exponentiation has higher precedence than plus, so it sits on top of plus because this has to be evaluated before it can sit on top of plus, because this will be the first to be popped out. And then you have E, this would go to the output. And then you have another exponentiation, which is right associated, so this would sit on top of the earlier left exponentiation operator. You have the operand F coming in, which is put directly into the output, and now you reach the end of the output. All you do is to pop out elements of the stack. So this is how you evaluate, this is how you convert an infix expression to a postfix expression.